Okay, so in this video, we are going to sketch a graph of the rational function y equals x squared over x squared plus 4. As always, the first thing we need to find are the first and second derivative. Let's find the first derivative. As we have a quotient, we have to use the quotient rule. So we'll get the derivative of x squared, which is 2x, times x squared plus 4, minus x squared, times the derivative of x squared plus 4, which is 2x, over x squared plus 4 all squared. As always, we're going to try and simplify, so we factor common terms. There's a 2x in both of these terms. It's common factor. We can factor it. And so we'll get a 2x. If we factor 2x, we're left with x squared plus 4. This is gone, minus x squared. Over x squared plus 4 all squared. Well, this simplifies quite nicely. X squared minus x squared is 0. And you have a 4 times 2x. This is an 8x. And we'll leave 8 up front as a constant multiple. And we're left with 8 times x over x squared plus 4 squared. So we now have our first derivative. And the reason that we leave the 8 as a constant multiple of the entire fraction is now that we are going to find the second derivative. 8 is just a constant multiple of the expression, so we leave 8 up front, because the derivative of 8 times this function is 8 times the derivative of the function. So we have 8 times. Once again, we have a quotient, so we use the quotient rule. Derivative of x is 1 times this. So x squared plus 4 squared minus this times the derivative of this function. Now we use the chain rule, so the outside function is the power 2 here, which will give us, if we differentiate, 2 times x squared plus 4. 2 minus 1 is 1. By the chain rule, times the derivative of the argument, which is 2x. All over the square of our denominator, which gives us the 4th power of x squared plus 4. Let's try and simplify and factor in common terms. Well, we have an x squared plus 4 here. We have 2 of them here, so we can factor one of them. So x squared plus 4. If we factor this one out, it's gone. If there are 2x squared plus 4 terms and we factor 1, we're left with just the 1. There are no other common factors, so we can combine. And we're going to have x squared plus 4 from the first term, minus x times 2 minus 2x times 2x is minus 4x squared. The whole thing over the 4th power of x squared plus 4. And now we can simplify. This is a power of 1. 4 minus 1 is 3. So this cancels this. And we have now a power of 3. And on top we're left with 4. X squared minus 4x squared is minus 3x squared. Oh, and I forgot my 8. The 8 stays up front. So we have 8 times 4 minus 3x squared over x to the 2 plus 4 all cubed. So x squared plus 4 cubed. And now we have our second derivative factored and simplified. Well, we have a quadratic here, but we'll factor this, find the zeros, when we look for our inflection points. So now we have our first and our second derivative simplified, so we're good to go. Let's look for possible zeros of our function. Again, since we have a rational function, the fraction can only be 0 if the numerator is 0. Therefore, if x is equal to 0, and we, at the same time, have found our y-intercept. When x is 0, y is 0. Every time you have a rational function, you have to be wary of possible vertical asymptotes, which means a division by 0. But here we have x squared plus 4. This is always greater than or equal to 4, and so we will never have a division by 0, so this function has no vertical asymptotes. So we jump to our critical points and possible inflection points. If you look at the derivative, critical points are points where the derivative is 0 or is undefined, but as x squared plus 4 is never 0, we will never have a division by 0, so y prime will never be undefined. So we have to look for critical points, solving derivative being equal to 0. But again, the derivative is a fraction. It can only be 0 if the numerator is 0. Therefore, if x is equal to 0. So we have a unique critical point, x equals 0, where, since the derivative is 0, where the function is flat at x equals 0. Let's look for possible inflection points now. Again, inflection points are values of x where the second derivative is 0 or is undefined. The only way that y double prime would be undefined is if we have a division by 0. But as x squared plus 4 is always at least 4, this will never happen. So y double prime is always defined. So we have to look for inflection points where the second derivative may be equal to 0. But once again, the second derivative is a fraction. It can only be 0 if the numerator is 0. Well, 8 times something is 0 if this term is equal to 0. Therefore, y double prime is 0 if and only if 4 minus 3x squared is equal to 0. Send 3x squared on the other side. So if and only if 3x squared is equal to 4. Divide both sides by 4, so x squared is equal to 4 thirds. If and only if well, if x squared is 4 thirds, x will be plus or minus the root of 4 thirds. And here if you want, you can say, well, the root of a over b is the root of a over root of b. So that's plus or minus root of 4 over root of 3. But the root of 4 is simply 2, so you get plus or minus 2 over root 3. If you want, you could rationalize and say this is 2 root 3 over 3, but we don't really care here. We'll leave it like this. So we have found two possible points of inflection. Well, then we want to try and classify our critical points. Since at x equals 0, the derivative is 0, will we have a local maximum or a local minimum? So we classify our single critical point. And again, because we're looking for concavity at this point, we look for the second derivative at x equals 0. Well, let's just look up what is our second derivative. It is right here. So if you plug in x equals 0, this is 0. You're left with 4 times 8, 32, divided by 0 plus 4 is 4, so it's just 4 cubed. And again, don't bother computing this and cubing 4. We don't care. All we ever care about is the sign of the second derivative. This is clearly positive. So the second derivative is positive, so the curve is concave up at x equals 0. But because the curve is concave up, and x equals 0 was a point where the derivative was 0, the curve is flat there and concave up, so we have to have a local minimum. And we also know that when x is 0, y is 0, so we can look at what the function would look like around x equals 0. The y value is 0. The derivative at 0 is 0, so the curve is flat there and is concave up, so we have a local minimum. So the curve would look something like this around x equals 0. And now that we have classified our unique critical point, we're now ready to build our table of values. Well, our first point was our 0, which was the same as the y-intercept, which was also our critical point x equals 0. And if you plug in, if you go back, this was also a 0. So we have the point x equals 0, y equals 0. We can remind ourselves that our function, y was x to the 2, sorry, over x squared plus 4. And we had, this was our unique critical point, and we had two possible inflection points in -2 over root of 3. And you'll want to have an approximation for this number. So if you use your calculator to find a decimal approximation, -2 over root 3 will be approximately -1.15. And we had, of course, the other possible inflection point in 2 over root of 3, which will, of course, be approximately positive 1.15. And if you plug in -2 over root 3 or 2 over root 3 in this expression, the 2 over root 3 squared will become 4 over 3. And if you compute, you'll have in both cases exactly 1/4. 1/4 is exactly 0.25. So we now have our table of values, our unique critical point, which was a local minimum, and our two possible points of inflection. And if you notice something about the points of inflection being the negatives of each other, it's not too surprising, because if you look at the function, since the only variable x is squared, whether you have an x or it's negative, you get the same y value, so the curve will be symmetric about the y-axis. And because we're squaring, if you look, x squared is always non-negative, same for x squared plus 4, so y will never be giving you a negative value. So when you sketch your axes, factor this in. So we have our x values of 0, roughly -1.15, 1.15. So let's go up to 3. So let's go with 1, 2, 3, -1, -2, -3. Our y values, at least for the points that we have in our table of values, for the critical and possible inflection points, y is 0.25, 0.25. So suppose this is equal to 1. This is 0.5, and this is therefore 0.25. And now let's plot our 3 points of interest. The point x equals 0, y equals 0. The point roughly 1.15, 0.25. So 1.15 would be approximately here. And 0.25 is here. And of course, the mirror point, -1.15, 0.25, so it'd be roughly here, -1.15, 0.25. So we have our two possible inflection points, and our unique critical point And if you remember, we found, after we classified it, that x equals 0 was a local minimum. So we glue this picture onto our point 0, 0. And now the question about these 2 points is the following. These were, if you remember, points where the second derivative was 0. So they are possible points of inflection. But how do we check whether or not there is a change in concavity for both of these points? Well, we are going to look at concavity at 2 and at negative 2 to figure out if there is indeed a change in concavity at these 2 points. So let's evaluate the second derivative at 2 and the second derivative at negative 2. Well, what was our second derivative? Let's go back. This right here is our second derivative. So if you plug in x equals 2, 2 squared is 4, 4 times 3 is 12, 4 minus 12, negative 8, times 8, negative 64, over 2 squared is 4 plus 4, 8, 8 cubed is a positive number, and you see that we have a negative over a positive, so at 2, the second derivative is negative. So let's forget the value. It is negative. Therefore, at 2, the curve is concave down. And what about when x is negative 2? Well, if you go back to the second derivative, you notice that the value of x is squared in both instances. So whether you plug in x equals 2 or negative 2, you get the exact same value. So the second derivative is also negative at x equals negative 2. Which implies that the curve is also concave down. So now we can look up and see, well, if you look to the left of this point, we know the curve is concave up, and at positive 2, sorry, the curve is concave down. So this will be a real point of inflection. To the right of our point, the curve is concave down, so concave down here, but to the left of our point, the curve is concave up. So there will be a change in concavity, so we have concave up, and we hit this point, and because we know that beyond 1, there are no other inflection points or possible inflection points, concavity will never change again, and because at 2, the curve is concave down, it will be concave down for every value to the right of our point, and so the curve will go from concave up to concave down at this point. And the same goes for negative 2 over root 3, right? The second derivative at negative 2 is negative, so the curve is concave down here at negative 2, but because to the left of negative 2 over root 3 there are no other possible inflection points, the curve will never change concavity ever again to the left of this point, and because at negative 2 the curve is concave down, it will always be concave down on the left of this point, but to the right the curve is concave up. So therefore this is a real point of inflection. So the curve is concave up, we hit this point, and because at negative 2 we have concave down, the curve changes to concave down. So it will be concave down forever. We hit the point, negative 2 over root 3, concave up. We hit the other point, 2 over root 3, and then concave down. And you see there are only 2 questions left over. To the right of this point, there are no inflection points or critical points. So the curve will never ever change its behavior again. It is increasing concave down. It will remain increasing concave down forever. To the left of this other inflection point, there are no other critical points or inflection points. Therefore, the curve will never change its behavior again. It is decreasing and concave down. It will remain decreasing concave down forever. So the only question left over is, well, what happens to our y values as x goes to positive and negative infinity? Therefore, looking for possible horizontal asymptotes. So let's see. What happens to y as x goes to positive infinity, and what happens to y as x goes to negative infinity? Well, our function was x squared over x squared plus 4. And in both cases, because we are squaring, we will have a positive over positive infinity. So we know that we can find the limit in both cases by multiplying top and bottom by 1 over x squared. Let's multiply out. We'll have on top 1, because x squared over x squared is 1. So 1 over x squared over x squared is 1 plus 4 over x squared. So simply 1 plus 4 over x squared, 1 plus 4 over x squared. As x goes to positive and negative infinity, because we are squaring, x squared also goes to positive infinity. Therefore, 4 over x squared will be shrinking to 0. And we're left with 1 over 1. So in both cases, the limit is 1. So you see, as x approaches positive and negative infinity, y approaches 1. So y equals 1 is a right and a left horizontal asymptote. So we can draw our asymptote. So y equals 1 will be a right horizontal asymptote, and also a left horizontal asymptote. So, as x goes to positive infinity, y will be getting closer and closer and closer to 1, always remaining increasing concave down. And as we let x go to negative infinity, y will also be getting closer and closer to 1. So maybe here I'll make it a little steeper, just to emphasize that we are approaching y equals 1. The curve should be perfectly symmetric about x equals 0, the y-axis. So imagine that this is slightly more symmetric. I've just here exaggerated to emphasize that we are approaching y equals 1 as x approaches negative infinity. And so we have now sketched a graph of this function fairly accurately. So let's include a few comments to this picture. As we have just said, y equals 1 is a right horizontal asymptote and a left horizontal asymptote. So the same goes for this part. Y equals 1 is also a left horizontal asymptote. Then what? These 2 points were indeed points of inflection because the curve goes from concave up to concave down, and concave down to concave up. So both 2 over root 3 and negative 2 over root 3 are points of inflection. And finally, we have classified the point x equals 0 as a local minimum, but it also is a global minimum, because for no other value of x will the function attain a smaller value than 0. So x equals 0 is a global minimum. And that's it. We have a really accurate sketch of our rational function x squared over x squared plus 4 using only the first and second derivative. We found that x equals 0 was a global minimum. Negative 2 root 3 and positive 2 root 3 were points of inflection. And y equals 1 is a left and a right horizontal asymptote. So that's it.